Hello and welcome to my channel on classical physics. Today we will be dealing with a very simple problem in center of mass linear momentum. This is a topic which finds application across a wide variety of problems. This is a very simple problem, and let's get to the problem here straight away. So we have two blocks of masses m1 and m2 joined together with a spring with a coefficient k, elasticity, and it so happens that the first mass is imparted a velocity v0 through an impulsive force, which means at an instant suddenly is imparted this velocity v2, thus mass m2. So the first thing we need to calculate is as to what is the velocity of the center of mass. Now this is a basic concept about center of mass. This exactly is the central theme of this concept. Center of mass is supposed to be that quantity of mass which, when assumed to have a velocity equal to the center of mass, conserves the momentum of the entire system of which the center of mass is being calculated. So the first thing which comes to notice, the first thing of note here is the linear momentum of the system. So first of all, we need to understand what the linear momentum for the system is. Now linear momentum of any body of any mass is just equal to the mass of the body multiplied by its velocity. So here in this case we will see that the first body is at rest. We are talking about that instant when the force and the velocity is imparted at that point, and the second body is imparted a velocity v0 instantly. So the linear momentums for individual bodies are equal to m1 into 0 and m2 multiplied by v0. So the linear momentum of the entire system is the addition of the two. The spring is massless here. Anyway, it will have a velocity 0 initially. So the entire system has a linear momentum given by m2 into v0. This is the linear momentum of the entire system. By definition, this should be equal to the velocity of the center of mass multiplied by the entire mass of the system. The entire mass m of the system is m1 plus m2. So what follows is that VCM into m1 plus m2 is equal to m2 into v0. So VCM is equal to m2 v0 upon m1 plus m2, which is the velocity of the center of mass for this system. So what follows is that as soon as this block is imparted a velocity v0 in the right direction, this block stretches forward. With it stretches the spring. The spring stretches, which causes a shift from its initial equilibrium position, and as we know that any spring when stretched opposes that motion, and this spring will try to contract itself and bring this block backwards. So as the spring's length is increased, there is a tension which will set into that spring. So we know that if x is the amount by which a spring stretches, the tension that acts on that spring is equal to kx. So let's assume that at any point in time, the spring has been stretched by a distance by length x. So let us assume that that is the point when the spring has stretched maximum. What we want to say here is that that is the point at which beyond which point the spring will start to compress, because what will happen in the system is that The block will move rightwards, the spring will stretch, but this stretched spring will exert a force on this block in this direction and in this block in this direction. So the spring will always try to contract itself, pulling both the blocks together. But this force will increase as the length of the spring is increased. So for a span in time, the length will keep on increasing because of the momentum of this block. But as that happens, the tension in the spring will start to increase as well, and that will cause a greater force acting on both the blocks, which eventually will mean that the process of lengthening of the string of the spring will stop at some point, and there will be a maxima reached for the length of the spring. So we have to calculate that length. So let's assume that length to be x. So if you imagine at that instant in time, when the length is x, and that is the maximum stretched length for the spring, at that point in time the conservation of energy would still hold. So the potential energy of the entire system would be given by half kx square for the spring. We know if x is the stretching, the potential energy is given by half kx square. So half kx square plus the kinetic energy for the system would be half entire system's mass m1 plus m2 multiplied by the center of mass velocity, which we calculated here just now. So half kx square gives us the potential energy, half mass into vcm square gives us the kinetic energy, and both of these will sum up to give us the entire energy of the system which is conserved, and which was half m2 v0 square initially. Remember that at this point in time the spring is not stretched, and hence there is no potential energy. So the only term for energy here is that of kinetic energy, and that too in the second block only, because the first block is at rest. So by using the conservation of energy, we can arrive at the value for x, which is the maximum stretching that the spring will experience. I would let you take a closer look. So here we have a very simple center of mass and conservation of linear momentum, conservation of energy problem. Hope you liked it. Please share it with other colleagues of yours, and till the next time, it's goodbye from me. All the best. Thank you.